Okay, good afternoon, everyone. For those who already watched my video, would you mind to help me sending the link to your friend? Okay, so we can start right away. Oh yeah, by the way, I need to remind you again that the attendance, you have to fill the attendance in academic.itb.ac.id. Okay, don't forget about that. I already opened it, and you are allowed to fill it until the today's class is over at 3 p.m. Okay, I will wait a bit until most of you already attend the class. Maybe one more minute and I will start it after that. Only 14 of you hosts has already watched my live video, so maybe we will wait another minute, okay? Okay, because half of the class already there, then I will start the class. Yeah. Yesterday we discussed about some of the problem. This is the first problem that we discussed yesterday, and this is the second problem that we discussed yesterday. Okay, and for both cases, the one in question is just stress distribution, not stress distribution, I'm sorry, normal force and shear force and moment at one particular point at this location, for example, D and E. Okay, but try to imagine if we have to find the internal force and internal moment, but not just at one point, but at all the members and at all location. For example, I want to see what is the internal force and internal moment at this particular location, this, all location, basically all location. How should we do that? Okay, because one of the way is you can make a cut here, continue with another cut here, another cut here, another cut here, here. But and you can continue to all parts of the member, but it will not be effective because there will be a lot of cuts that you have to do, and you have to solve a lot of equations as well in order to solve that. Okay. So for today, we will try to concentrate on how to find out the internal force distribution of a member. For example, for this member, for example, AB member, all the internal force distribution will be like what? And all the internal moment distribution will be like what? At all location. That's the thing that we will try to concentrate today. Okay? Up until this point, anyone want to ask question? If there is a delay between what I talk about and what is there in the YouTube, okay, what you can do is you can ask me directly in the statics group. So if you have any question, you can ask me directly in the static group, but you can also ask me via the live chat in YouTube as well. So it's up to you. Okay. So that's the thing that we will discuss today. But before that, I want to ask you first whether you understand about the things that we will discuss today. Any question? Not yet. From Mirza, not yet. Anyone else? If you have any question. That's the problem with YouTube, right? Okay. In that case, if there is no question, I will continue with the how can we find the stress distribution. Okay. Argi Rafidan, excuse me while I eat rendang. Yeah, you can. That's the beauty of online class, right? You can do anything you want while watching my video. So you can do that in your bedroom, you can do that in your couch, you can do that wherever you want, and you can eat while watching me as well. It's up to you. Okay, let's now let's try to discuss on how can we find the internal force and internal moment. Okay, as usual, I will remind you again about the sign convention. Okay, I will remind you again about the sign convention. So, as usual, the sign convention is like this. Positive moment whenever we analyze the right side of a particular cut. Okay, the moment will be counterclockwise, positive. The shear force will be going down, and there is another one. The normal force is supposed to be going outwards. Okay, and on the other hand, if we want to see the left side of a particular cut like this, okay, the moment is supposed to be clockwise like this, positive, and the positive shear force is supposed to be going up, and the normal force is supposed to be going to the left because it's going outward. Okay, then this is it. Okay, if we want to see a particular structure, for example, if we want to see if there is this kind of structure and it's under distributed load, random distributed load, something like this, And now we want to find, okay, the internal force which is happening at the whole member, the whole part of the member. This location, this location, this location, all location. Okay, how can we do that? Before we try directly to that, I need to tell you about the secret thing on the relation between shear force and internal shear force and internal moment. Okay, for example, if we want to take a look at this small element here, okay, and then I zoom in to that particular small element. Okay, as usual, at that element, if we see the left side of the cut, because I cut that particular element, and I want to see the left part of the cut, this part, okay, and the right part of the cut, okay, okay, as I told you before, at the left side of the cut, there will be internal force and internal moment, okay. The positive direction for the internal force is supposed to be going up, and I name it as V. And the positive, sorry, I forgot to draw the stress. Sorry, not the stress, but the W. Okay, and I forgot to draw the dimension as well just now. I'm so sorry. The length of the element is dx. Okay, and on the left side of the cut, okay, this part, there will be positive V going upwards. Then there will be another moment, positive moment, going counterclockwise like this. There will be no normal force because there is no external horizontal force. So I will neglect that. I will ignore that first. Now, if we see the right side of a cut, okay, this part, I need to draw the positive direction of the what will be there as well. There will be shear force as well here, and there will be moment as well here. Okay, positive moment. Counterclockwise, positive moment, and the positive shear force will be going down. But the magnitude, it won't be just V here for the shear force, but it will be V plus dV. Why it's like that? Because there will be slight difference between the shear force here on the left side and the shear force here on the right side. That's why the difference there, I call it as dV. That's why I name it as V plus dV for the right one. And for the moment as well, there will be slight difference, m plus dm there. Okay, because the actual magnitude will be slightly different in this case. Now, the first thing that I want to do is I want to find out the relation between the internal force and the external distributed load, W. Okay, how can I find that? I can do it by using sigma Fy equal to 0. By using sigma Fy equal to 0, okay, by using sigma Fy equal to 0, what will I get is there will be V going upwards, positive. Okay, positive is going upwards, okay. V going upwards, positive. Then there will be V plus dV going downwards, negative. And there will be W going downwards as well. But for W, because this is a force equilibrium, we have to multiply W with dx. So we will have like this, w dx equal to 0. Okay, I'm so sorry, it's quite hot here, so now let's continue. What we will have here will be, the phi will be gone, so what we will have will be minus d phi will be equal to w dx. Okay, so this is the first relation. This is the first relation between the distributed force W and the internal shear force. Okay. If you are a little bit confused on the application, later we will try to discuss about some problem example using this. Okay. Same as here. W will be equal to minus dv per dx. Yeah, the same. W here will be the same as minus dv per dx. Okay, so this is the first equation that we have. Okay, up until this point, anyone want to ask question? You can ask me directly via YouTube, or you can ask me via live chat in the YouTube or via WhatsApp. "32 viewers." Okay then, it's getting bigger. You are supposed to listen to me, not supposed to discuss with your friend in the live chat, okay? Don't discuss about the rendang, okay? Okay, any question? Pak WDX itu dari from Agung, from Derajat, oke? Okay? WDX itu dari F sama dengan WX, W kali DX. Betul sekali. WDX itu munculnya, bener Agung, bener Derajat ya. Ini di sini WDX. Kenapa di sini muncul WDX? Oke, betul sekali. WDX itu munculnya karena gaya yang diakibatkan. Sorry, I supposed to speak in English. WDX here appear because the force due to the the external distributed force W, it will be W multiplied by dx, right? That's it. Because the element is small, when we have the length is only dx, means that the element is very small. Because the element is very small, that's why we can assume that the shape is close to rectangular. That's why we can get the force by just the force due to W is the same as W multiplied by dx. That's correct. Mirza, can we have the example? Later I will give you the example, but for now, try to accept it first about the equation, because I need to tell you guys the derivation of the equation first. Before after this, I will go to the example, problem example. Oh, about Muhammad Abdul Malik, can you please repeat about phi plus dv if you don't mind? Okay. For phi plus dv, why it's phi plus dv here and why it's m plus dm here is because we know, okay, the left part and the right part, the moment the internal moment and the internal force will be slightly different. There will be slight difference between the internal force on the right and the internal force on the left. And there will be a slight difference as well between the internal force, the internal moment on the right and the internal force on the left. That's why on the right, I assume it as V plus dV, and on the for the moment, I assume it as M plus dm, and on the left is just V and M. Just that. Victoria Emanuela. So how do we determine the direction for the V and moment if we get it wrong? Is it okay? Better not. Okay, Victoria, better not. Because as I told you, whenever we start a cut, okay, whenever we start a cut, for example, right, I want to cut it like this here. Okay, whenever you start a cut and you analyze the cut, okay, at the right side of the part where you cut, okay, you have to always, wherever is it, you have to always assume the positive direction, because it's on the right of a particular cut, the V will be going down and the moment will be counterclockwise. Always like that. So we always assume positive direction here, because if not, later you will confuse yourself. Okay, any other question before I continue with the relation between the internal moment and the internal shear force? Any other question? Okay. In that case, I will continue. Yep, correct, Victoria Emanuela. So the right side of the cut goes down for the shear force, and the moment is counterclockwise. Yes, it's correct. Because as I told you before, we follow this sign convention. At the right side of a cut, this one, the shear force is going down, for a positive shear force is going down, and positive moment is going counterclockwise. But on the left side of a particular cut, this one, okay, the moment is going clockwise, and the positive moment is going clockwise, and the positive shear force is going up. Okay, for both, the internal normal force is supposed to be going outwards. Okay, any other question? Yang tutup dong. Okay, then we will continue with the next one. The next one will be the relation between moment and shear force. Okay, the relation between moment and shear force, we can find it by, wait, let me wipe this one. Okay, the relation between moment and shear force, we can find it by doing the sigma moment on the left side. Okay, sigma moment on the left side, okay, equal to 0. By doing so, what we will get will be, here the moment due to V will be 0, the moment due to M they will be there. Okay, positive is clockwise, so M will be there. What else that we have? We will have another clockwise from V plus dV. phi plus dv multiplied by dx. Then another one minus m plus dm. Okay, due to this one. It's minus because it's counterclockwise. Then due to w. Due to w, as usual, because it's distributed force. And at the beginning, I told you that in this kind of small element, dx is very small. That's why the distribution of w can be represented by a rectangle. So the moment due to w will be, the force will be w multiplied by dx, okay? And the moment due to w, it's supposed to be w multiplied by dx and multiplied by the moment arm. And the moment arm here will be dx per 2. Because the centroid of this particular w will be exactly in the middle, dx per 2. Okay, that's why we will have it here plus w multiplied by dx multiplied by dx per 2 equal to 0. Okay, one thing that you should remember here is dx, dm, dv, all of those are very small because the element size is very small. Okay, dm here will be very small, dv here will be very small, dx will be very small. So if you have a very small value and you multiply it with another very small value, in that case we can neglect that particular multiplication. So for example, here m will still be there. Okay, phi dx will still be there, but dv multiplied by dx, both are very small values, so we will ignore that. So we will not count that. Then we will have m minus m here, and we will have minus dm here, and then the last one, w multiplied by dx multiplied dx per 2, dx multiplied by dx. So very small multiplied by very small. So we will neglect that as well. Will be equal to 0. This and this, we can cross it out because it's minus each other. So at the end, what you will get is phi dx is equal to dm. Okay? That's why we can write it down that phi will be equal to dm per dx. This is another equation that you should know. Okay, until this point, anyone want to ask question? Raffi Saludin. Okay. Pak, I still don't understand. Which part you don't understand, Raffi? Any other question? Okay. I believe this kind of thing will be confuse you quite a bit, but try to accept it first. Later, we will try to implement this in the real problem. So I believe you will get, you will have more understanding later after we try it directly in the real problem. Everything, sir. Okay then. In that case, it is better for us to directly go to the problem example after this. Okay. Why are we talking the total force distribution at the middle of it's not equal equally distributed. Oh, Abiyat, why are we talking the total force distribution at the middle? Okay, so although it's not totally equally distributed, not constant like that, we can assume it in the middle because the element is very small. Because the element is very small, okay, the difference between the value of W here and the value of W here, okay, the value of W here and the value of W here will be minimal because the element size is very small. That's why we can assume that the value of W here and the value of W here is more or less the same. That's why we can assume that the centroid of the distributed force is exactly in the middle. So the moment on that question on the middle, why did you multiply by dx per 2? On the middle? No, I calculated the moment to the left side. Nope, I calculated the moment to the left side. So the moment to the left side, like this, okay, the moment to the left side, okay, due to v plus dv, okay, due to v plus dv, we will multiply it by dx. Okay, due to v plus dv, we will multiply it by dx because the distance between the left side and the right side will be dx. So v plus dv multiplied by dx. Okay, for the moment you don't have to calculate, multiply it with anything. Then for the distributed force, okay, for the distributed force, the force itself due to the distributed force will be w plus dx. Okay, but the moment will be w multiplied by dx multiplied by dx per 2 because the centroid is exactly in the middle. We assume that the centroid is exactly in the middle. If the centroid is in the middle, the distance between the left side and the middle side, the left side and the middle will be dx per 2. That's why this one, dx per 2 is there. That's why we have it like this. Okay, Nadia, sorry. If dx is so small that it becomes negligible, why do keep? No, dx is very small. Okay, but we still have to calculate that. Okay, we can only neglect it if we multiply very small value with another very small value. Okay, so we can't neglect that when we have v multiplied by dx. V multiplied by dx will still be there. But if you have something like this, dv multiplied by dx, yes, you can neglect that. Okay, if you have something like this, dx multiplied by dx per 2, yes, you can neglect that because it's very small to multiply with very small. If we neglect everything, we don't get anything Abiyat. So we can only ignore the thing that is very, very, very small. Okay, Nadia, can you repeat what happened to the moment due to W? Why did it disappear in the second step? Okay, at the second step, the moment due to W disappear because, okay, there is W multiplied by dx multiplied by dx per 2. dx is very small value, dx per 2 is very small value. So this calculation will be very, very, very small. That's why it's negligible. I want to neglect that in order to make the calculation simpler. Okay? Yep, dx square is negligible. Correct, Abiyat. Dx square is negligible. Okay? If it's just dx, you still have to put it there. But if you multiply dx with another dx or dv with dx, yes, it is better for you to neglect that. It's negligible. Okay? The thing that you learn up until now is just a very there are a lot of simplification there. So it will only work for very small deformation case. Okay. Later, if we have another case which has a very large deformation, this equation will not work anymore, and it will not be part of statics and mechanics of materials subject. It will be part of the advanced mechanics of materials, which you can take it in the master program. So we actually not supposed to neglect it for large deformation. For small deformation, like in our case, we can neglect it. Okay, in the large deformation, all those things that we neglect before will not be neglected, but it will not be part of our study in statics and mechanics of materials. So for those who are interested in statics or mechanics of materials, you can study further in master program, and you can take advanced mechanics of material, which will discuss about this in detail. Okay, any other question? Okay, for Rafi, don't worry, Rafi. Okay, if you don't understand later about this, we will still be able to use the final equation. Okay, the thing just now is for some of you, I believe for some of you, you can understand how can I get this particular equation and this particular equation. But for some of you who don't understand, just accept it that the relation between W and dV is like this. The relation between W and V is like this, and the relation between V and M is like this. Okay, just accept it. So in the real case later, what we can do is just use the equation directly. So for this one, I just explained to you how to get this equation, that's all. In future questions, are we given dv, dx, dv, and dm? No. You are not with CC, okay? We will not give you dv, dx, and dm. But dv, dx, and dm, we will use that in the integration of the equation that we will use. Later, I will explain it in the problem example. Okay? So, I will continue a little bit. Okay. Now we know that W, the relation between W and with V is like this. This is the first relation, W equal to minus dV per dx. And the second equation will be V is equal to, V is equal to dm per dx. Okay. What we can get here is, if we have the equation of M, okay, if we know the equation which govern M, okay, later we can find phi by doing the first derivative like this. Okay, and on the other hand, if we know the equation which govern phi, okay, we can find M by doing integration. Okay. Okay, the same as this one as well. If we know the equation of W, we can find the equation which govern phi by doing this, minus W dx. That's the thing. Okay, So this is the relation that you're supposed to know. Yeah. And the slides here will be more or less the same. Okay. When you do integration, what you will have is something like this. So phi here will be phi naught minus integral the integral of w dx. Okay. So I suppose to change this one. This one is supposed to be m naught plus integral of phi dx. Okay. And this one is supposed to be phi naught minus integral of w dx from x naught to x1, from x naught to x1. This is it. So this is the final equation. The same for the moment. It will be like this. Okay. This is the equation that you need to know. And beside that, because we can find m by doing first derivative, sorry, we can find phi from the first derivative of m, then, and we can find w by first derivative of phi, we can find w by doing the second derivative of m. Okay. Muhammad Abdul Malik, is the moment from the left equal to the moment from the right? What do you mean by that? I don't understand. The total moment supposed to be 0. That's the thing. The total moment supposed to be 0. But the left moment and the right moment is slightly different. But the total moment, the sigma moment equal to 0, sigma moment equal to 0 will still be there. Arik, you can do whatever you want as long as you watch my video. Okay? Because I believe some of you are a bit confused about it. Let's try directly to a particular problem. Okay? I want to try to solve problem from here. This one. Okay? This is a problem example. The one that is asked there is we have to find the internal force distribution and internal moment distribution. Okay, we have to find the internal force distribution and internal moment distribution for this particular for this particular case. Okay, let's try to solve it together. Four kilonewton is 4 meter here, 6 meter here, and there will be like this and like this. Okay, AY, AX, BY. As usual, whenever you have problem like this and you are asked to find the phi distribution and moment distribution. Okay, for problem like this, what you can do, okay, as usual, try to find out the internal force, the external forces which is happening there, AX, AY, BY. Okay, what you can do there first is to try to solve for AX, AY, and BY. Okay, after you solve for AX, AY, and BY using sigma Fx equal to 0 for this free body diagram, sigma Fy equal to 0, and sigma moment equal to 0, using these three equations, we will be able to get the value of Ax, Ay, and By. Okay, using sigma Fx equal to 0. What you will get is Ax is equal to 0. Okay, and using sigma moment at A equal to 0, what you will get will be 6 meter multiplied by 4 kilonewton, okay, minus By multiplied by 10, okay, supposed to be 0. And we can find the value of By. The value of By will be 2.4 kilonewton. Okay, then using sigma Fy equal to 0, what we will have will be 4 kilonewton minus 2.4 kilonewton minus Ay equal to 0. Then we can find that Ay is the same as 1.6 kilonewton. Okay, all of this you have already learned it before in order to find the external force. Now let's find the phi distribution and the m distribution, the shear force distribution and the internal shear force distribution and internal moment distribution. How can we find that? Okay, now our new free body diagram will be like this. Our new free body diagram will be like this. Ay here is 1.6. By here will be 2.4. Then we have 4 kilonewton. Try to solve is the shear force, and then after that we will try to solve the internal moment. Okay, how can we find the distribution? Now, as usual, we can cut it. The first cut is here. Okay, using the first cut, we can draw the free body diagram. Okay, and the things there will be 1.6 kilonewton there, and there will be internal force and internal moment at this side. But one thing that you have to remember, the distance here, because I can cut it everywhere here, the distance here, I assume it as x, which means that I cut it at the x distance from the left side, from the left edge. Okay, this is the distance from the x, the distance from the left edge here, the distance from the left edge here is x. Okay, why I have to assume it as x? Because it has to be able to represent all the points here which means the cutting location is a variable. This one. The cutting location is variable, x there. And then at the right side of the cut, we will have phi going down, positive, okay, and moment going counterclockwise, positive. This is the first cut that we have to analyze. Up until this point, anyone have any question? Please try to concentrate. Don't concentrate on what I'm wearing. Yes, I know I'm using 3 stripes clothes. So what? Okay. Anyone want to ask question up until this point? You can ask me via WhatsApp or you can ask me via YouTube chat. Laswardi salam alaik. How about the normal force, sir? Okay. The normal force, you can draw it as well there. N here. But the problem here, like it or not, N here will be 0 if we use sigma fx equal to 0. Right? That's why from the beginning, because there is no horizontal force at all in this particular free body diagram, that's why N, I don't draw N because I know from the beginning the N will be exactly 0. But if you want to draw it in order to ensure that everything is there and everything which is supposed to be there is there, you can as well. But using sigma fx equal to 0, my result will be N equal to 0. But you can draw it. No problem. Any other question? Sir, can you repeat the cutting parts? Rajat, okay. The cutting parts, I can cut it everywhere that I want, right? And the cutting is supposed to represent all of this location, right? All of this location. The cutting is supposed to represent all of this location. That's why what I can do is I cut it randomly like this here at point 1, okay? But I assume the location of where I cut it is x, which is a variable. Because later I want to find the phi in terms of x, the m in terms of x, and n in terms of x. Because I want to draw the stress distribution. I want to draw the force distribution and moment distribution. That's why, like it or not, I have to have a variable x, where x is the location where I cut it. So I just cut it at one location, then assume that I cut it at x like that. Okay, Derajat, can you get it? Okay, if there is no more question, I will continue. Because I know from the beginning that n will be 0, then we will not calculate n anymore here. That's why I just delete it. Okay, now let's try to calculate phi. Okay, using sigma fy equal to 0. If we use sigma fy equal to 0, what will I get here is 1.6 minus phi equal to 0. In this case, phi is the same as 1.6 kilonewton. Right? Then, I will continue. with sigma moment at the left side, sigma moment here, at the left side here, equal to 0. What will I get there? I have to ignore the 1 kilonewton, 1.6 kilonewton on the left, but I can't ignore this one, phi, because I know already the phi is 1.6 kilonewton. So if positive is clockwise, what I will get is phi multiplied by x. In this case, we already know the value of phi, right? Okay, then minus m supposed to be equal to 0. But phi, we already know the value of phi. Here, this one, 1.6 kilonewton. So 1.6 x minus m multiplied by 0. That's why we can find the equation of m here, 1.6 x. This is it. This is the equation that I want. That's why if we want to draw, okay, this one is not important anymore. Okay, that's why I will just delete this. That's why if we want to draw the shear force and the internal moment, we can draw it like this. Okay, this is my shear force, phi, okay, and this is my moment here. For the shear force, it will be 1.6 kilonewton. For the moment, it's supposed to follow 1.6x, which means, okay, at x equal to 0, the value will be 0. But at x equal to 6, okay, at x equal to 6, this one is x in meter, at x equal to 6, 1.6 multiplied by 6 is supposed to be 6 plus 3.6, so 9.6, right? It's supposed to be 9.6. 9.6 kilonewton meter. Okay, unfortunately for us, one cut here will not be enough because there is a 4 kilonewton here. Okay, there is 4 kilonewton at the distance of 6 meters from the left. That's why we have to create another cut. This one, at this location. But for this particular cut, the distance will not be x anymore. X is supposed to be the distance from here to here. This one is x as well, right? So if I draw the second cut, okay, if I draw the second cut and I want to see this free body diagram, it's supposed to be like this. .4 kilonewton. I try to see the right free body diagram. Okay, this particular cut. Okay, and the distance here, it will not be x because x is from the left side to the cut. So because the distance was 10 meter, The distance is 10 meters, so the distance here is supposed to be 10 meters minus x. And then on the left of the cut, we can draw the positive direction. V is going up and moment is going clockwise. Then we can do another, the same as like this one, but on the right free body diagram. On the second free body diagram, this is the first free body diagram, this is the second free body diagram. On the second free body diagram, we can do the same. Sigma Fy equal to 0. By doing sigma Fy equal to 0, what will I get is V plus 2.4 equal to 0. Then my V will be minus 2.4 kilonewton. That's why we can draw it here. It will be minus 2.4 kilonewton. Then using sigma moment, okay, sigma moment from the left side again equal to 0. What will I get will be moment, clockwise is positive, moment minus 2.4 multiplied by the distance 10 minus x equal to 0. Then my moment will be, this one is 2.4. 2.4 multiplied by 10 is supposed to be 24 kilonewton minus 2.4 x. This is the equation for the V. This is the equation for the M. To continue this one. Okay. Now this equation will only work at x equal to 6 until x equal to 10. That's why we have to check at x equal to 6. Okay, so this equation, the first one just now, it will work for x equal to 0 until x equal to 6. The second equation, on the other hand, will work for x like that. That's why now we have to check the value of m here, because we know that this is linear equation. The value of m at x equal to 6 and x equal to 10. At x equal to 6, you can substitute the value here. What will I get will be 24 kilonewton meter. This one is supposed to be kilonewton meter, okay? I made a mistake. 24 minus 2.4 multiplied by 6. What is that? 24 minus 12, 14.4. I believe it's supposed to be 9.6, right? So exactly at the location where we left before, and at x equal to 6, at x equal to 10, what will I get here? The moment will be equal to 0. Right? 2.4 multiplied by 10 will be the same. Will be 24. 24 minus 24 will be 0. So This is my graph later. This is 10 here. So the final graph will be, for the moment, will be like this. Okay, for the shear force, it will be like this. Any question here? Big Boss MV. Okay, Raffi as usual. Okay. Wallahi sir, I wish I understand all of this, but I don't. Don't worry, Raffi. As long as you practice more and more, you will be able to understand body. Okay? As long as you practice more and more, you will understand body. Sir, but we said before that the equation for moment distribution is m equal to m0 plus integral v dv. Does that just mean mo here is 0? That's okay. Habiat. So basically, there are several ways to solve it. The equation that I told you just now, we can try to analyze it after we know one of the equation. For example, just now we do it this way, right? For m, we're supposed to know the v first, okay? Because there is no w in our case here. Because there is no w in our case here, what we can do is we have to find the phi distribution first. Okay, we have to find the phi distribution first. Let's check the phi, our phi value. Okay, our phi value here is 1.6 kilonewton from x equal to 0 until x equal to 6. And then our phi will be minus 2.4 kilonewton from x equal to 0, x equal to 6 until x equal to 10. Then, if we take a look at the moment, okay, the moment here is supposed to be the integral of phi. Okay, the moment there it's supposed to be the integral of phi. Let's try to implement this. Let's try to implement this in order to get our moment distribution from phi distribution. Okay, so our moment distribution for x equal from 0 x to 6. Okay, the first one, the left cut, this one. Okay, this one. For this one, from 0 to 6, what will I get will be m equal to m0. Our m0 is actually 0, right? So let's try. m0 is 0 plus integral from x0. Our x0 is supposed to be 0. Okay. X phi. Our phi here is supposed to be, just now our phi value is 1.6 kilonewton. I'm so sorry. 1.6. Okay, dx. What we will have here, okay, what we will have here, it will be 0 plus the integral of 1.6 dx will be 1.6x, and the limit will be 0 to x. In this case, our results is 1.6x. You can see here, it is exactly the same as this one. So actually, what we can do is we can use the integration method like this, like what I told you at the beginning. We can solve it using the integration method, or we can solve it using the cutting method like this. So there are two different methods that I talked about just now. The first one is the cutting method, and the second one is the integration method where I told you at the beginning. Muhammad Abdul Malik, can we do moment from the right or only able from the left? You can do it from the right or from the left as long as it's consistent. It's supposed to be okay. Fire breathing rubber duck. Okay, it's Asa by the way. Yeah, just the same as Big Boss, right? Whenever online you use some other's name. Okay. I'm sorry, my other account error. So sir, for the attendance, I'm here yesterday too. By the way, don't forget about the attendance. You have to open the academic.itb.ac.id, and you have to mark your attendance there for this particular class. So the attendance supposed to be done by yourself. Wilma, sir, can you explain again where you get x equal to 6 and x equal to 10? Oh, from the integration method, how do we know that m0 is 0? Okay, from the integration method, how can we know that m0 is 0? Is you have to calculate the the internal moment at the left end here. Because there is no external moment there, most likely your internal moment on the left side will be 0. So your m0 will be 0 here. M0 will be 0. If there is a external moment on the left side here, okay, on the left edge here, external moment on the left edge here, your m0 will not be 0. It will be the same value as what are the external moment there. Wilma, sir, can you explain again where you get x equal to 6 and x equal to 10? Okay, I will explain again. Why x equal to 6? The limit here is y is from 0 to 6, not 0 to 10, because you can see that the continuous condition will only happen from x equal to 0 to x equal to 6. Because at x equal to 6, exactly at x equal to 6, there are external force of 4 kilonewton there, which not will make the condition continuous. If the condition is not continuous, your equation will not be able to be derived directly. So that's why in this case, what I do is I create two different cuts. On the left of the 4 kilonewton force and on the right of the 4 kilonewton force, this one. This is on the left of the 4 kilonewton force and this is on the right of the 4 kilonewton force. Okay, why 10 meter? Because the length of the bar is 10 meter. So if you see the phi distribution, m distribution here, for example, if I want to see the shear force distribution at this particular point, what I can do is just to draw the dotted line like this. Okay, so this is the value of the shear force at that particular location, and this is the value of the internal moment at that particular location. That's the use of drawing the internal shear force and internal moment diagram. So we can analyze at all of the location here. Oh, okay. Okay, that's what my friend used to call me in high school, sir, big boss. Okay, but unfortunately for you, Rafi, I will not call you by that name. Okay. Muhammad Arfan, I think x equal to 6 is the length from the left side to 4 kilonewton. Yes, it's correct. Yes, it's correct. Just now I explained again, right? Because there is a 4 kilonewton at x equal to 6. That's why the equation will not be continuous. We will not be able to create a continuous equation from the left side to the right side. Okay, from the left edge to the right edge. Okay, so what we can do here, there are two different continuous equations. The first continuous equation is from x equal to 0 to x equal to 6 meter. And the second continuous equation is from x equal to 6 meter, this one in the middle, at where 4 kilonewton is, to x equal to 10 meter. That's why I created two different cuts like this. The first cut is in the middle between x equal to, not in the middle, but around between x equal to 0 to x equal to 6 meter. And the second cut here, this one, I cut it between x equal to 6 meter to x equal to 10 meter. Okay, that's why there are two representative equations for phi. So we can write it down like this. Okay, for phi, okay, between 0 to 6, the equation will be phi will be 1.6 kilonewton, and between 6 and 10 meter, phi will be minus 2.4 kilonewton. Okay, for the moment, the equation that we will have between 0 to 6, the equation will be 1 how can I, yeah, from 0 to 6, what will I get will be 1.6x. Moment will be 1.6x. And from 6 to 10, the moment will be 24 minus 2.4x. That's the thing. This is the final answer. Anyone want to ask question? Why we cut it between 4 kilonewton? Yes, of course we have to, because just now I already explained, right, Muhammad Arfan? Because 4 kilonewton force makes the equation will not be continuous, because it's concentrated force. Concentrated force or concentrated moment will create a discontinuity in our equation. That's why we have to do the cut in between the external concentrated force and external concentrated moment. Okay, because our final aim is to create the internal force distribution and internal moment distribution. So we have to get the equation like this. Any other question? Any other question? Sir, I still don't get why the normal force is negligible. It's because it's very small. No, CC asked me via WhatsApp. Sir, I don't understand why the normal force is negligible. The normal force is not negligible, but actually you can put the normal force here. But at the end, the result will be the normal force equal to 0. That's why I don't want to draw it there. Because I know from the beginning that the normal force will be equal to 0. But for you, because sometimes you don't know about it, it is better for you to draw it like this. Okay, you can draw it. This one is normal force here, and here there will be another normal force. This belongs to the right one, and the other one will belong to the left one. You can draw it like that. Okay, but at the end, what will I get will be here, n is equal to 0, and here n will be equal to 0 as well, using sigma fx equal to 0. Oh, Abiyat, yes. Abiyat is only answer it for you. Yep. Then what about when x equal to 6 and x equal to 10? Okay. That's very good question, Abiyat. That's very good question. When x equal to 6, exactly at x equal to 6, exactly at x equal to 10, it's out of our scope. Because it's exactly where the concentrated force happened. So it's outside of our scope. We will not talk about that, especially for the fee, right? For the fee, we will not talk about that because it's supposed to be you're supposed to get it in the advanced mechanics of materials. Wouldn't that mean we ignore the effect of 4 kilonewton? No, we didn't ignore the effect of 4 kilonewton because in order for us to calculate, in order for us to know the external force the external force at the left edge and the external force at the right edge, 2.4 kilonewton at the right edge and 1.6 kilonewton at the left edge, we calculate the effect of 4 kilonewton there. So the effect of the 4 kilonewton is actually there. But we will not discuss further about what is the shear force at exactly 6 meter. No, we will not discuss about that. And we will not discuss as well about the shear force, what is exactly the shear force which is happening at x equal to 0 or x equal to 10 meter, because it's where the concentrated load is. Okay, you will learn about that in advanced mechanics of materials. Okay, derajat GK, what does GK means? Okay, any other question? Okay, if there is no question, after this I will give you some homework about how to find out how to calculate the internal stress distribution, internal shear force and internal moment distribution when the concentrated external load is given. Okay, I will give you a homework on that, and please submit it to me before Thursday. And on Thursday, we will discuss about what will happen if the external distributed force is given. Currently, we are only discussing of the case where this will be one of your homework later. Okay, we are discussing only where the case of if the only concentrated force is given to the external load. But we are not yet talking about if the stress, if the distributed load, something like that, is given to the structure. What will happen there? Okay, we will discuss about this next Thursday. Okay, but for now, I will give you some of the homework related to this. Related to if we give external concentrated load to a structure, how can we draw the internal force and internal moment distribution? Okay. I think that's all for today. Don't forget to take your attendance for those who come to who watch this video at this hour. Okay, I will open the uh, the attendance until 3 p.m. So please mark your attendance in academic.itp.ac.ad before 3 p.m. today. Okay? See you guys next time. Bye.